like a carbon steel or mild steel as we call it. I can confirm this because I've tested at least over 1,000 of these stuff. Nevertheless, you're asking about Young's modulus. What Young's modulus basically is, you see this line from year to year, right? This part over here. Okay, so we deem that as a perfectly straight line, and each gradient, right, which will be, assuming this is the stress and strain graph, right, is going to be there's something called the elastic modulus or the Young's modulus. You got that, right? So what I'm saying to you, do you know when you have a straight line in math, something like this, you know, y equals mx plus c? Are you with me, Cleo?
Yes, sir.
Yeah, you're aware that the gradient is the same. It doesn't matter which 2 points you take. It's a slope of the graph. You got that?
Yes.
Yeah, so what I'm saying that if you take any point, like let's say you take this point, right, and that point, right, like this value and that value, right, you should get the same value. If you take that point and that point, you should get the same value. If you take that point and that point, you should get the same value. But that only exists within the limit of proportionality, or this part over here. You cannot do the same thing once you come on this side, because over here, this is essentially called the plastic region. This is permanently deformed. So what I'm saying is that any value within this region, you're able to find that over there, because this is actually the gradient of that line. I don't know if that's clear.
Yes, it is, but like
Yeah.
the force of that, sir, because they give you the force of limit of proportionality. Do you use the same force, or do you find the force of basically that
So
triangle that you
yeah,
draw
yeah. So
straight
what
up?
you're gonna do is convert your force when you got there, right? So obviously the stress and strain graph is basically the same as the force in the area graph, right? Okay, in terms of how it looks. This is change of length, which you guys call x, right? Let me just do that quickly. So what I'm saying is you're gonna have to go stress. I mean, my bad. You're gonna have to go. You have to calculate the stress. Oh, this is my razor. So you got your force. Don't worry. I think I have an example like that. But stress over, you're gonna have to find out. You're gonna have to find out your stress. You know what I mean? You're gonna have to find out your strain at that same point, which will be the change in length over length.
Mm,
And once you have
mm,
both of them, you can calculate the elastic modulus. You got me.
okay.
And if you're having problems with it, you can just put it on the group, and I can definitely solve it. It's really no train smash. Yeah,
Okay.
yeah. Like I
Okay, no
said,
problem.
this
Thank you,
is
sir.
yeah. This is not even yeah. Just ask. You should. And you'll be surprised at the questions you get. Okay, guys, welcome. I'm just gonna do a quick intro about myself, and then we can begin. I think it's just worth mentioning who I am so you can see, and then I want us to solve the problem immediately. I want to see where you guys are at, and then we can always have a chat afterwards if you guys do want to have a chat about certain stuff. Um, but what I can tell you while I'm looking for this thing now, is that strength of materials is a very tough subject, and that is not there to motivate you, just that it requires a lot of time. Yeah, my success rate has been fairly good. That's what I'm hearing according to the thing. But yeah, let me just quickly tell you who I am, and then yeah, so you can actually have a look. But again, I'm just your tutor. I don't work for the same organization which you do. As I mean, as Northlink where you're studying, but I mean, I'm obviously as a support function. So I'm just gonna share that with you. It's not gonna take me that long. And then you can just see what I'm about, and we'll engage. Okay, cool. Let me just share my slide here, go, and then we can begin. And again, guys, please stop me. If I'm here to support you guys. Okay, cool. Just confirm that you can see this. Can you guys see it?
Yes, we can see.
Okay,
Well,
cool.
I can see.
Thanks. Okay, cool. Anyone else? Aiden, Pusisiwe, Rafika, and who else joined now? Akif. Okay, cool. So, guys, that's me, eh? That's me when I'm fresh, right? Um, Qualifications, got a national diploma at CPT, I have a BTEC at CPT, got a master's at CPT, focused on energy. I might be conducting other research. Yeah, that's where I'm at with my qualifications. Experience, I've worked 2 years, just 2 point something, but 2 years basically at a pressure vessel manufacturer. I was literally testing materials. So all what I've done was probably a lot of the first few chapters with a lot of, and with welding, a lot of stuff I can mention there. Worked in a similar capacity at CPUT, and then I started lecturing eventually in 2019 at the mechanical and also the marine engineering departments. I've lectured a multitude of subjects. You can see over there. Strength of materials is one of them. I lectured at least 3 semesters, I think. And then I'm also registered with EXA. I'm not sure if you guys are aware of that. He's as a professional engineering technologist. That is, I got that this year. I'm also council member at the Institute of Engineering Technology. So if you ever want to register with EXA, maybe get your PR Techne. Yeah, I can give you some guidance on things like that. And obviously, I've worked on a lot of other projects, which I'm not going to mention now. Um, um, the latter part, the former part used to be with materials, and I'm going to solar thermal. And then I've some of my research interest anyway. So that's me, right? So I'm just gonna stop that. So you are probably in one of the best hands. I'm sure of that. Yeah, I've only had good feedback from the other students. I've been doing this since last year. So yeah, this is my 1, 2, 3, the 4th time I'm doing it. I'm trying it a bit differently this time around. Yeah. Anyway, so what I've done is I put these questions on the Google Classroom. And so yeah, I'm planning to do as much as I can today, right? By the way, on the Google Classroom, I have organized everything for you over here. That thing must come here. These are the stuff I've done through the other semesters. I do have all my recordings on my YouTube channel. I don't want to say it's a YouTube channel like I'm a, but it's there. It's like a suppository. And it kind of follows all the sessions over here. So I thought I'd do it a lot differently this time around. We don't have so much sessions. But anyway, everything is here. And if you guys have questions, you can always just ask. So I hope you guys can navigate this thing over here. So the question for today will be this over here. They will all be under module 0 moving forward. So you just got to open it up. And then these are the 4 questions. So I'm going to start with this one. And then I'll move to this one. This is from the Wickens textbook. That's from the toy textbook. This one's from a past paper, and this is also from a past paper. So yeah. I think that's okay. So let's begin with the first one, right? And again, you can just ask questions as you go along. Normally I still like, you've obviously seen how the other sessions were done, so I'm assuming you went over that, which makes things a bit easy. Just gonna erase this, and we're gonna just start solving immediately. And if you're not sure, just ask while I go along, so I can see what you know, what you don't know. Yeah. Okay, I'm just prepping the question quickly, and then we'll begin.
Sorry, sir.
Yes, Rafika.
Where do you log on to for this, the Google Classroom? Is it the same as, is it the LMS?
Yeah, it's basically like an LMS. So I sent the link some time ago in the group. You'll see it there.
Okay.
Yeah.
Okay, thank you.
Yeah, you can do it while I'm talking. You'll see, or while the others are busy.
Okay.
Yeah. Cool. So let me just share my whiteboard quickly. Can you guys see my whiteboard? Yeah. Are you happy with this? Can we see it? The question?
Yes.
Perfect. Appreciate that. Okay, let's move. But yeah, okay. So I don't know. I'm assuming you guys went over the theory. I'm assuming everyone has understand what this is. If not, I'll probably have to go back and talk about it. I mean, and I have that issue, which I shouldn't be doing. But anyway, let's move along. So here we have a aluminium alloy test piece, 12 mil diameter and 60 mil gauge length, and it's tested to fracture, always the case. The following results were obtained: load at the limit of proportionality, the extension at the limit of proportionality, the maximum load, the fracturing load, the extension and fracture, and diameter fracture. Are you guys interested to see an actual report done by students this year with something like this? You guys want to see it? You can say yes or no, or we can start solving.
Yes.
Yes. Anyone else?
Yes, sir.
Okay, cool. Thank you. Yeah. I just want to open up something. I'm going to open the report now. So I want to show you what this actually looks like. You know what I mean? It's actual results. I'm just going to open it up. Okay. Let me see. Perfect. Okay, it's going to come now. So these were submitted this year with marine engineering students. It's the standard test they do as part of their, the assessments and stuff. Okay. So I'll show you. Cool. Go out is opening. So what you're gonna have to see is a report. Can you guys see it? You guys see it over here? Tensor test. I'm highlighting stuff. Can you guys see it?
Not yet, sir.
Okay, cool. Let's see the sharing. Let's see. It's like a Word document, man. Yeah. Not yet, not yet. Let me see. Let's do this again. Now? Yes.
Yes.
Perfect. Okay. So I'm not going to take you into the particulars. I'll show you exactly what the specimen looks like, right? So this is just the preamble. So this over here, right? You see this over here? Just make it big for you. This is not a standard specimen, but that is what the specimen what they're talking about. It has a diameter of, I think it was 12 mil. The machine they used was something like this. This is a Hounsfield testing machine. Just bear with me here. And you got these two supports where you clip in the specimen. This support stays stationary, and this crosshead or this head moves basically up, pulling the specimen. So these are actual. So what the students have done is taken the dimensions before the test and eventually after the test. It's an aluminum 6082, by the way. So you can see that fracture you see over there. You'll notice this particular cup cone fracture. Anyway, so that's that. And then to show you what the actual graph looks like, it looks exactly like this. And the reason why I'm mentioning this to you is that you'll notice that for aluminium, it doesn't have a particular defined yield point like when you're doing steel. That's typically the things for non-ferrous metals. But anyway, that's what a graph looks like. Maybe one day I can show you guys, maybe I can actually show you the test myself. And this is a standard mild steel, a low carbon steel. And you can see that, that dot, that thing over there, the dip, and it goes up like that. Yeah, and then this is the summarized results, which this part is incorrect. So as you can see, this is something which is done. So just to recap on this graph while I'm here, if you're looking at the aluminium graph, and all specimens behave differently, but it looks the same. So this line from here to here, that is what we call the limit of proportionality, and that's where we find the Young's modulus. Around about this point, once it passes it, it's past the yield, and once it's past the yield, what it means is that it will not go to its original state. So what I'm saying is if you load the thing to around 150 megapascals and release the force, it will go back to its initial state. However, if you increase over this one over here, it will not go back to its original state. Anyway, so as you pull it, it goes, and eventually comes here and it just breaks. So yeah, I'll show you some kind of small simulation of what it looks like. But anyway, so that's some real results for you. Yeah. And by the way, and the results given is not a stress and strain graph. It's actually a force and extension graph, but you won't see the raw data presented. It's somewhere. Yeah. And these are just the initial diameter, the initial length. Once we were done, they were done. The final diameter was this. So you can see that this is that reduction in area they talk about. You have the initial length and you have a final length. It's all basically the same thing with others. And can you see these calculations? I'm sure you've seen it before. Yeah. All right. Without further ado, let's begin solving the question. Okay. See here. Whiteboard. Okay. So I have a whiteboard shade now, so hope you guys can see it. So let's quickly just draw the line and then we can begin. I'm just gonna draw a dummy graph here. It's an illustration. So it looks something like that. That's an accurate look. So anyway, so what they want here, and you don't have to do the graph, but anyway. So let's quickly find the stress at the limit of proportionality, right? So that's around here. So I mean, let's assume it's around here. This is the limit of proportionality. So let's say it's 1.0 So here they give you a load at 28. Let's call that force and extension. Doesn't mean it's the highest point, but anyway, I'm just going with that. So that's 28 kilonewtons. That's kilonewton, and that's in millimeters. And this corresponding point to be around 0.19. So that is 10 at 0.19 millimeters. So how do we find the stress? You guys know the relationship between can you guys find do you know the formula for stress first of all?
Force
Aiden,
over area.
thank you, Cleo. You guys all know that? Hope you guys do. If not, welcome. So again, when they're saying limit of proportionality, you want to use the values given over here, right? You don't want to use the other values. The maximum load occurs over here, just to talk to it now. So that's max, and the fracturing load, just drop that a bit, will occur over here. Okay. Just be cautious. So the limit proportionality is within this section over here. It can be anywhere here. So it's force over area, straightforward. So we look at what is this? The load, which is 28 kilonewtons. Okay, and then you want to divide that by the area. Now the area is it's a round specimen, right? And so therefore it's going to be pi over 4 d squared. In this case, it's a 12 mole, so you can represent it as 12 times 10 to the power negative 3. Okay, he's just lagging a bit. Okay, like that, and you just square. Instead of 12, you can just write 0.012. You know, you guys are comfortable with different things. Okay, so can you guys work that out for me? And if you're uncomfortable with the calculator, you can always just ask me to show you. Yeah. But when you come to my sessions, we're working. It's not talking, we're working.
So is it 247.57 for MPa?
Yeah, there we go. Okay. Can we confirm Cleo's answers? I don't trust her. Right? I want 2 more other students to tell me. That's megapascals, no? Okay. Should I calculate it for you, students? Or are you guys good? For me to calculate it, you can just say yes. If not, then yeah, you can just give me the answer. So I'd like to hear at least 2 other students, maybe Pussy and Aiden, to maybe yeah, get me those answers. Guys, are you there? Is Cleo my only student here today?
Different answer, sir.
Same answer, Pussy, yeah?
Yes.
Perfect. You could calculate it, no?
Yes.
Okay, perfect. Akif and Aiden, Rafika.
That's the correct answer.
Yes,
sir.
sir. Take the answer.
Okay. Yes, we can. Let's move along. So now the next part, right? It's asking for the Young's modulus. Okay. So there's a lot I can talk to about there. Just remind me to maybe talk to it afterwards. I'll just make mention right now that all materials have a unique elastic modulus. Not a unique, but different value. So what I mean is for steel, you could get anything from 190, 210 gigapascals. For aluminum, you can get anything around 60 to 675 gigapascals. And then I can't remember what the other one was now for copper. But anyway, so they all have different values, and I can show you the table if you want. But the relationship to find the elastic modulus or Young's modulus is basically stress over strain. Okay. Do we know how to calculate the strain, colleagues? What is the strain? Does anyone know?
It's the length over the change in length.
No, it's the other way
Okay.
around. Yeah.
Oh,
So it's a change in length over the length. Okay. All right. The change in length over length. Okay. I don't know if you guys are familiar with this. Do you guys like deltas at all? What is it called now again? X. It's called X here, no? X over L. Yeah, there we go. So it's the change in length over the length, right? And I'll show you what I mean by or the limit of proportionality over here. You never work with any of the other values besides these ones. Oh, I want it to be clear. So the extension they're referring to, oh, what happened there? Is that an error now? Okay, there we go. It's quite strange. I want to work with these other values, but you want to work with these ones over here. So fortunately for us, I come back over here. We have calculated the stress already. All we need to do is calculate the strain. And the strain you want to, the value you want to take is extension, the 0.19, and you want to divide it by the original length over there. You see there? So that's 60 mole. So you can either keep it in millimeters or you can keep it in, or you can put it in meters. So I think that was, okay. Can you guys hear me? Is that a bit of a glitch?
Yes,
then?
sir.
Yes, sir.
Okay, perfect. So you're going to take the 0.19 and you're going to divide it by 60. Okay. So 0.19 and you're just going to divide it by 60. Cool. So what do we get for the strain? By the way, it's a dimensionless unit because it's millimeter divided by millimeter, and therefore there's no units. I'm just making you aware. So it's just a number. So what is my strain? Is that Busi? I can't hear you.
3.167, sir.
3.167. 3.167.
Yes.
0.
That's correct.
What? 3.167.
Yes.
Times 10 to the negative 3.
Oh, okay. 167. Oh, that's what I was looking for. Yeah, times 10 to negative 3. Okay, did we all get that? 3.167. That's fine. We all get this.
So I just have a
Okay.
question.
For sure.
If they don't give you either like the length of proportionality and the
Mhm.
original length, either one of that, can you use the formula E is equal to force times length over area times the extension?
The free
But
formula.
like,
Yeah.
yes. So like,
Okay.
which force are you going to use for that? If you have two forces in that case.
So it's not that you have two forces. You must just be aware what force means what. So this force over here is a limit of proportionality, right?
Yeah.
The maximum load is at 52. Just, I'm not to scale here, so you must just bear with me. That's 52, right?
Okay.
And then this guy over here is 40. So it's more about you must know at which point of the graph you're working with to use specific values. I don't know if I'm clear.
Oh,
You know what I
yes.
mean? Yeah.
Yes.
So this over here, they should have called this the ultimate tensile strength, and this is typically the max. You see over here. Then we're talking about fracture, we're talking about where the specimen breaks. You see what I'm saying to you? So it's like at different points of the graph. That's how it works. It's not two conflicting values, it's two different values. Yeah. Okay. So once we have that, we've got the strain, we've got 2, and now we just got to put this into our calculator, 247, right? 0.57 times 10 to the power 6. And then we then divide this by, you know what I mean? By that over there. So that's 3.167 times 10 to the power negative 3. And our answer should be 10 to the power 9, which is GPa, gigapascals. Can we quickly confirm that?
What did you say the answer was, sir?
I'm not sure. I'm waiting for you guys.
Oh.
I'm trusting you. Yeah. But it's aluminium, so I'm expecting a value between 65 to 75. Yeah. In a practical setting, I'm not sure what's happening with this calc question. Yeah. You got a value for us, Cleo?
So I'm getting the same value as I got for E when we calculated it with 0.9.
Yeah, that's over here.
0.19
That's over
divided
here.
by 60.
Okay, no, so that's
Yes.
3.167, right? So now you're taking the stress dividing by the strain now. Have you done that?
Oh, no.
Yeah.
I'll just do it quickly.
So I got 0.078.
It shouldn't be 0.0. Just be careful of your, this must be 10 to the power 6 now, and that must be -3. It must be times 10 to the power 9. Yeah.
So
Yes.
why do you have there by the 2? Why do you have a times 10 to the power of -6?
It's not -6, man. It's just 6. Give my ink blob there. Yeah.
I've got 78,173 to the power, your times 10 to the power 9.
Yeah, 78. 173.
78,173 times 10 to the
Perfect.
power 9.
Yeah. Or instead of saying that, we can just say gigapascal, right? So
Okay.
that's the same as GPA, because 9 is giga. Okay. We all get that. What is confusing you guys? It's not a -6, man. Just watch out my handwriting. Don't trust my handwriting. Please. Just follow the logic.
But why
That's-
didn't you use the value you got that when you worked out the stress? Why did you write it to the power of 6? That is what I don't understand.
Okay. So is it Rafika? Eh?
Yes.
So remember, mega is 10 to the power 6. Are you with me?
Yes, I
You see this
understand.
over here? Yeah. So
Yes.
that's why that's to the power 6 as well. But we don't
You have
write
to
10
put
times
it
power
in
6.
like that.
MPA.
You have to put it in by 10 to the power of 6. You have to put that in. Why can't
If
you
you don't-
just put it 2
Okay.
247.574?
Because this is like a million, eh? You know what I'm saying to you? And this is 0.0 something. So these are very important. So what I'm saying is what this value looks like is like this. 2.475700012345 Are you with me? Not 2.2.24. Let me remove the point. It's like it's 2 million. That's why. And this over here is 0.003167. That's what it looks like in the normal decimal form. Are you with
Okay,
me?
it's fine. Yes, it's fine. I understand.
Yeah, it's not. So what this is, I hope I did this right. This is just a shortcut to write. You know what I mean? It could be another 0 here. It's just a shortcut to write. Let me just show it to you, man, because yeah. But colleagues, do you guys get that 78 so long? By the way.
So
Yes,
Okay,
sir, we got
perfect.
it.
Okay, let me just attend to Rafika quickly. Yeah, you're gonna have to.
Sorry, sir.
Yeah.
Just one more thing. When it came to the 10 to the power 9, I got 10 to the power
Yes.
10. Why does that
Okay.
change? Because there's a
Okay.
lot of
I'll
answers I saw after I do it a couple of times and it does that.
I'll sort you out right now. No? So let me just go to Rafika
Okay.
and I'll come to you right off. So I'm gonna share my calculator. Okay. So don't
Okay.
worry.
Thank you.
You can see now. So let me quickly work out the stress value for. I can show you what I mean. So just give me that force value again. What was it again? The force value. It's 28, no? Okay.
28 times 10 to the power 3.
Okay, so I type in 28. So you know what that is, right? Rafika, 28
Yes, I understand.
is
Know what that-
28K. You know what I mean? You see what I'm saying to you, right?
Okay.
So if I type in 247, just an illustration, 0.557 times 10 to the power 6, can you see what I'm talking about? It's a big number. We're just representing that as, are you with me now?
Yes, it's fine. Thank you.
Yeah. So you must have times 10 to the power 6. You can't just put in those values. Okay. So I'm gonna go to Cleo's question, right? So Cleo, have you ever wondered why this was here on your calculator? You see this over here? At ENG.
Yes.
That ENG is something called engineering notation. I'm not sure if you guys have covered that. I'm sure you guys have covered scientific and engineering notation. But nevertheless, so if you put in 247.57 times 10 to the power 6, then you can say 3.167 times 10 to the power -3, and you press equal. You get a 10 value, right? So what ENG does, engineering notation, basically just makes it power 3, power 6, power 9, power 12. You understand? All you do is press this bad boy here, and you get the 9. Are you with me? Got that?
I got it, sir.
Yeah, so if you want 6, you press that. You see there? If you want 3, you press it again. You see?
Okay, I see. Okay.
Yeah.
Got it.
Thank you. Perfect. Okay, so let's quickly do the next one. I'm going to the next part now. Okay. So I think the other should be easier. Right. And so anyway, so now we have to find the tensile strength. Again, I'm not happy with the wording here. This should have also been called the ultimate tensile strength, right? It's called the UTS. Yeah. Let's probably show you a report after this, but anyway. Okay, so the UTS, what it basically is, the UTS corresponds to the max load. You see here, the max load, which is that over there, not the fraction load, the maximum load. So all you must do is take the maximum load now and divide it by the same area. Is that clear, students? That's what the UTS
Yes,
is.
sir.
Okay, just quickly do that for me. I'll just keep the question so you can see it.
So with regards to that, the nature of that force, when it comes to
Yes.
you writing down the answer with the MPA, will you say
Yes.
that it's in tensile or negative or positive?
I like that to bring that because we're doing a tensile test, we don't have to worry about that now. That becomes more predominant in like the temperature stress part here. But you can write plus. Plus means tensile, negative means compressor. But I mean, it's a tensile test, you know what I mean? So
Yes.
yeah. But that's a very
Okay.
good point though. Yeah. Okay, let's quickly work that out. You should get that answer. You can ask me like 1,000 questions. I'll probably answer all of them. I've done this so long. So yeah,
So
you can come. Yes. Bring it.
when it comes to getting the stress of this, you get 10 to the power 3 and then 10 to the power 6. Are you allowed to write it in gigapascals?
Always write in
Or
MPA.
would you?
So keep
MPA,
stressing
okay.
MPA. I can explain to you for days why, but you want to keep it MPA, you know? And for
Okay.
E, you want to keep it GPA.
Okay.
Okay, yeah. That's how it typically, yeah, just the thing is when you buy materials, man, you'll see on the spec sheet MPA. You know what I mean? I'll show you proper material sheets, man. You'll see like it's like you know, if you go buy something and you say you want a 2 centimeter round ball, the guy will look at you like, what are you talking about? We don't talk in centimeters, we're talking millimeters, you know, as an engineer. You know what I mean? Or M8 bolt or whatever. It's not in centimeters. So MPA is like the material way of talking, you know, like it must have a UTS of so much MPA. I don't know if I'm making sense, but yeah. Okay. Did we get the 66 to 8.76 colleagues? Aiden, Pussy, Akif. Should be easy to do.
So is the force 10 to the -3 or 10 to the 10 to the +3?
So remember what kilo is, eh? It's times 10 to the power 3. The force is always big. You know, kilonewton. You know what I mean?
Okay, so
Yeah. It's never negative. It's not negative, but it's a big force. It's kilo, you know?
I got 459,781
Perfect.
megapascal.
Yeah, that's fine. Yeah. Maybe Boosie's here. She's making our life easy. Guys, you can just check check your answer as well with Pussy. That's on there. I'm not going to calculate that one. That should be easy to do.
So can she explain how she got to that, please? Sir?
No, I can show it to you. Don't worry. Don't worry if you need to. All right, I'll show it to you. I'll show it to you. I just thought that we could all do it. Let me just quickly come to it quickly for you. So I'll say that again. So for the tensile strength, that's the it's supposed to be called the ultimate tensile strength. That's the max load, and it corresponds to the maximum load the specimen has taken. Admittedly. So 42 kilonewton, and you divide it by the same area as the previous one over there. So I'll write it out for you over here. Okay, just give me a second. 8.3 is force. I normally supposed to be called UTS subscript. And then the force was given as what? 52, eh? Let's go back up. Yeah, 52. And if you worked out the area here already, it's basically the same area. This one over here. I don't know what's the value of it. But you're just going to say again pi over 4 d squared. I think it's a 12 mole size. Okay, if you got it there, you should get that answer.
Yes, sir, I got that, sir, but I didn't get I got 549,780,
549. What is it? Yeah, it's correct. Yeah, 549.
259. So, but so can you just do that the answer, please? Because I don't get that answer. I get a bigger answer, sir.
You don't get 459.
I also get a bigger answer.
So I get 459,780,946.
That's fine. What's big about that?
So, but then if I divide it again by 1,000, so then it will be gigapascals.
No. This is, you said it's 459 point what? 7?
No, sir. 459,780.946 megapascals.
Oh, okay. I see what you're saying. So let me just work out and show you what I mean. What did they do to you guys in Info? Jeez, man.
So I also got 46017.99
times fine.
10 to the power 3.
If you close, it's fine. 450,
Okay.
460, 49. Yeah, I'll show you now. Let me just do my calculator again. You must remember something about engineering, science, particularly. It is representing physical phenomenon. So yeah, it's not a mathematical game. Yeah, so I'm just making you aware. So you always have to kind of understand what you're doing. You can't just cram this thing. So 52 kilonewtons, are we happy with that there? Right? Are we happy?
Yes, sir.
Okay, cool. Just keep talking to me. Yeah, pi over 4. Let me go that. You can go 0.012 if you want. And we're just going to square him, right? So we square him, you say equal. You see that you get that? I press my ENG, I get that. You see, I don't know. That's it.
So sorry, is there a way you can just show us quickly on the calculator how to store the values again? I forgot that method.
Okay,
So
I'll
that
show you the story
it'll be
now.
easier. Okay.
Okay. But can you see this? Is everyone happy with that calculation? It's only to archive quickly. Are you sorted
Yes,
now?
sir. Yes, sir. I'll see.
Yeah.
I'm going to double check now, sir.
Yeah, okay. So if you want to use storing quickly, just as a throwaway, let's say I want to store my area, right? Is that fine? Right? Clear. So it's power over 4, 0.012, and I want to square him. Is that fine? That's my area there, right? Got it?
Yes,
Again,
sir.
you want it like that, you can put it like that. Okay, so now if I want to store this, I go Shift, Store, and I press either A, B, C, or D, E, or F. So I want to store it in A. You see there? And I press A. So that means I store the answer in A. Is that clear now? I'm going to show you now. You got
Yes,
it?
sir.
So now let's say you want to recall the
Yes.
value of A. You got alpha A, you press equal, it comes back up. You understand? If I got
Yes,
alpha
sir.
B,
Got it.
my bad, it's alpha B. Alpha B, there's an alpha B here. It's not going to work because it's alpha B. I don't say nothing because I didn't store anything in B. Does it make sense? So if I do redo the
Yes, sir.
calculation, I can just say 52. You know what I mean? Like that. All I can say alpha what? Alpha A, right? Which is that value stored, done. Press that. Same thing. Are you content?
Got it, sir.
Perfect. Okay. So we have, you got this answer? Let me share again. Yeah. Let's go back. Okay, I'm not going to write it down. You guys can do that. So the next part of the question is the following. Now they want a true or actual fracture stress, right? This is not a metric we typically use in the practical things. It does mean something, but nevertheless, let's quickly work it out. So the actual stress is basically with fractures, right? So it goes up, gets up max load, and eventually comes down and it breaks at a particular point, just over. So what we then have to do now, we have to use now the fractioning load, right? The 40 kilonewton. But now we have to use the diameter at fracture. Are you guys with me? We don't use now the 12 mil now. So now you must use the 40. You must find a new area at 9 mil. Is that clear to everyone? That will be your fracturing stress. You guys got it? So it's the same calculation. Force over area.
Yes, sir.
But just different values. If that makes sense. Yeah. Quickly do that for me. You don't know right now, but your body is studying right now. I'm preparing you. So make sure you work with me. I want to show you the elongation. That's something.
I got 6288.319 times 10 to the power 3.
Okay, 6288. Yeah,
Yes.
but you can press E and G again, and then you'll get 6, I think. Oh yeah, just check. But that looks like to me, yeah. That's fine. As long as you're close, they'll mark you right. It's not a problem. Yeah, you can't be just way out. Just wanna use this here. Okay. Let's confirm with Cleo there, guys, please. Okay, what 6 to 8 something something.
Yes, the answer is right.
Okay, perfect. Yeah. Dr. G is joining us. Dr. Gulabella. Okay, are we happy with that? Could we all get 6 to 8.76 megapascals?
Hello, sir.
Hey, good evening, doctor. Good evening.
Thank you. I must study now to get that
100%.
down.
Exactly. we must go there. We're going there. Yeah.
Yeah, thank you, sir. I was just passing by. No.
No problems. Okay. So did we all get that 628.76 megapascals? Colleagues? Akif, Cleo, Rafika,
Yes, sir.
Lucy.
Yes.
Okay, 100%.
Yes, sir.
All right,
Yes, sir.
so let's do the percentage elongation and the percentage reduction in area. So these metrics, they tell you whether we are inductile in nature or brittle in nature, right? So typically over 20% percentage elongation is deemed to be greater than 20%, or from 20 going up is deemed to be ductile. I don't know if you guys are familiar with those concepts, but yeah, there are those concepts of ductile and brittle. Likewise with the percentage in the reduction in area. So if you watch the videos, I do kind of talk about that, I think. So the percentage elongation, what it basically is, I think it's in a formal sheet. I just don't like how this is being written. So we're basically taking the change in length of the whole thing, right? The total change in length, and you're dividing it by the original change in length, and you're timesing it by 100, right? That's a percent. So I'll just quickly do that one. So that's going to be 8.5. Cool. So if I come here, we look at the extension at fracture. So that means at this point, right? we've extended a total amount of 8 millimeters. So what I mean is that, let's say we had a specimen like this initially, right? Oh no, I must be careful. Is that a change in length? That is, that's the, yeah, okay, let me just see. Yeah, so this is 60 mil, right? And then after the test, it was now kind of like that, something like that, right? And now between these two shoulders now, it's 68 millimeters. Are you guys with me? So it is extended by 8 mil. So to find the change in length, you're basically going to take the 8, extended by 8, divided by the original, which was 60, and you're timesing it by 100. And you just get your answer. Is that all? That's all, guys. So just quickly get that answer.
13.33%.
Perfect. Percent, no? That's a percent, eh?
Yeah.
Yeah, okay. That's in a percent value. I think we all can easily do that. I'll just wait on everyone. Just let me know once you've got it, and then we can move on to the percentage reduction area.
It's 13.33, sir.
Okay, perfect. Perfect. Okay. I think that's enough. You guys can quickly do that other one. So the reduction in area, reverting back to my suspect specimen, is that we look at the initial diameter. All right, so that in this case we had 12 mil. And then at this particular, let me just make this less thick here quickly. Like at this point, after fracture, we put the specimens back together, and then we measure the vernier, and then you notice it's basically 9 mil. So it'd be 9 millimeters after fracture. Okay. Cool. So we have that. So now we're going to see how much the area is basically reduced. So it's quite simple. We just basically say percentage reduction in area. I'll just call it RED. And that's going to be the big D squared, your initial, right? Am I right? Is the initial minus the final squared. And then, yeah, it's going to be divided by the initial again. So all squared, eh? So there was pi over 4 on each one for the area, but we just obviously cancel them out. I don't know if that makes sense to you guys. Mathematically speaking, is a common factor. So all we do is take the initial diameter, which was 12. We can just keep it in millimeters. We don't have to change units. The final diameter was given as what again? It was 9. It was 9, right? 9 squared. And then we just divide that by 12 squared. And then now we've got our percentage reduction in area. Just work that out for me. And you have to practice.
43.75%.
Perfect. 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 Just wait on the others to check. All the past papers have a lot of these, a lot of this type of my tab is not working anymore. Damn. Okay.
That answer is correct. Sorry, that answer is correct, sir.
Sorry, I got kicked out there. I'm gonna share again. Did we all get that 43 something?
Yes.
Okay,
Yes,
perfect.
sir.
Okay. So yeah, we're done with that one. Answers are all correct. So I just want to quickly show you something over here. Yeah, that's just I'm not going to talk about this, but anyway, this is me working back in the day. But I wanted to show you an actual mold test certificate. And if you look at the certificate, this is a steel oh, I think unshared by itself now. Okay. Okay, let me just do this again. Still I am recording. Okay, just give me a second. My Adobe, something's wrong with my Adobe. Okay. Give me a moment. Okay, share again. Just want to show you what our actual material test cert look like. So you can see. Then we'll do the compound part next. Okay. Cool. Sharing now. So I'm sharing a presentation. You can have a look at it. Cool. Okay. This is the wrong one. That's fine. So another one. Can you guys see my slides?
Yes, sir.
Okay, perfect. Okay, so I'm gonna show you what it's up. Okay, first things first before I get there. Just to quickly talk about these values. So if you look at the far right over here on the table, you'll notice different E values, as I was mentioned to you, timber, right? Type of
So
wood.
we don't see your table, sir.
Not yet there. Now,
No, sir. We just see your cover page.
okay, it's probably lagging. Oh, let me just start to reshare. I think my OneDrive is full, man, so my whole thing is lagging. Okay, can you see it now?
Yes, sir.
Perfect. So if you look at the far right, can you see aluminium around 72, whatever alloy that is, brass around 100, 102, cast iron 90. So can you see how all of them have different, you know what I mean? So-called unique properties. Yeah. That's that point I wanted to show you. And then this is just what that was. And then again, specimen, we put it back together, and that's the small diameter over there. That's a reduction in area. Again, that's the change in length as well. And then what I wanted to show you was actual material test set. That's what it looks like. There's an actual material test set of this material over here. And you can see for this cost number over there, tells you this is a plate, tells you your, okay, you shouldn't trust China too much, but anyway, that's your yield stress of 558. That is your tensile strength of 678. That's your percentage elongation of 29%, and that's your rock hardness of that. And there's also some other tests done. So can you guys see those properties over there? So when you buy a material, even at Maxsteel, you can request this, and they'll actually provide you with this. Is that okay? You guys got that?
Yes, sir.
Okay, perfect. And whatever material you get, it should come with a test certificate like this. Yeah. Okay, so this is also a test certificate of which what I've done. This is a duplex stainless steel, which I actually tested back in those days, 2014. But anyway, yeah. So you can see over here, I didn't need the yield, it wasn't in question. What is just important? I didn't even need the elongation. But the main parameters for this particular test was your UTS over here. Yeah, so these are all omitted. So duplex stainless steel, check there around 748. This is a very strong value. Can never do this. Okay, so let's quickly go to compound bars, which will be the next part, basically. Yeah. So There's two arrangements you must know. I'm sure you got to look at it. Let's quickly just start to go through it and then we can solve that one problem. So on the left, you'll see Akif on a swing, right? And you notice there's two ropes, right? Where Akif is holding, which is essentially supporting the weight of the boy. So I want to ask you from a force perspective, if Akif is sitting on a sheet, obviously the gravitational force is going down, right? How are the forces shared between the two ropes? Is it the same or is it different or what? Assuming they're different, of course.
Isn't it? Is it 2 times the weight?
Wouldn't say 2 times the weight. I mean, we can't say that yet.
Oh,
Is it the same or different? It can't be 2 times the weight because that's more force. Yeah.
Mm.
But I'm asking, is it being shared or not being shared? Or is it the same or not the same? Just using logic. You know what I mean?
It's equally distributed. So.
Okay, you say it's equally distributed. I don't necessarily agree with. If it's two different materials, will it be equally distributed? So let's say you had one steel and one.
Oh, it's two different materials. Oh.
Yeah, are you with me on? So if it's two different materials, what happened then? There's steel and then there's like a normal rope,
is it
which will carry more weight.
the one with the less, with a smaller diameter?
That's a good point also. That's a big factor. That's good. Okay, we'll talk about it. Yeah, that is a factor. One smaller one might have more stress, yes. Okay, so I explained to you. So this over here is a parallel arrangement. This over here is a series arrangement, meaning that this one and this one follows each other, like two shafts. And let me just give you the maths because I see time is coming here. So for a series arrangement, right? And they're saying, in the previous slide, they say each rope carries the entire weight of the boy in this configuration. So all the forces down is equal to all that forces up. And they're saying if one rope fails, then the ball will fall to the ground. Therefore, FA is equal to FB equals to FT. So the total force transmitted through the whole rope is the same. Think of this like a current. Like think of force like a current, right? However, they're saying the weight of the boy will stretch the compound rope, which is this rope. And they're saying that means that each rope will carry, each change of length will be different. So you have to add them all up and you'll get a total change in length. I hope that's clear to everyone. So you got to add the first one, you got to add the second one, and give the total extension. However, on the left, where Akif is sitting, the forces are, we have to add them up, right? So they're saying since two ropes carry a portion, and this is what I was looking for, of the boy's weight, the sum of the forces upward in each rope must be equal to the weight downward. So if one rope fails, the other rope might still be able to carry the boy's weight. Therefore, the force A plus the force B must equal the weight of the boy, which is essentially the force total. So we see FT is actually the weight of the boy. Same time, they say there, the weight of the boy causes the rope to stretch a certain amount. Each of the two ropes will stretch an equal amount. Obviously, we're assuming the ropes are of equal length. Therefore, as he sits down, they will both extend by, let's say, 20 more equally. I hope that's clear. So these relationships are very important over here. Okay? So know what the difference between a series and a parallel arrangement is. Okay? I hope we can see this to a degree. So let's quickly do a problem without wasting time. Okay. I'll give you obviously engineering type problem now so you can see. It's the next one. Have you guys taught on compound bars yet? Rafika, Aiden, Akif, Pussy?
No,
Have
sir.
you guys... Yes. Oh no. I just missed you.
No, sir.
Okay. Okay. Damn. Okay.
Yes, sir, I did.
Okay, cool. But you saw the other video post today, which talks to that.
Yes, sir.
I do recommend for the test, hint, nudge, make sure you understand parallel. Is that clear?
Yes.
For the up and coming test,
sir.
yeah.
Thank you, sir.
Okay, cool. Yeah. No stress. So make sure you understand it thoroughly, not copy and paste method. You understand it, and we'll do one now. See time. Let's just get through this one. What am I looking for? Sessions. Okay. So this one is coming from Peter Toit, a textbook. Yeah, I recommend you get that one. I like that one more. Cool. Let's quickly see here. I could have chosen a more simple example for this, but I thought you guys went over it. But anyway, here we are. Okay. So here we have some kind of.
So your
Could have
screen is
been-
frozen, so.
Okay, cool. I'm gonna share it now. Don't worry. Can you see it now?
Hello?
Nothing yet?
Yes,
Right.
sir. Got it, sir.
Okay, perfect. I think I should have chosen a more simple example, but this is what I'm gonna have to do. Okay, so here we have this 3-post support and I-beam. This is a bit more advanced problem, but yeah. Okay, anyway. So then we have some UDL load on top of here, right? And they're saying the central post is a steel post in the middle and 2 aluminum posts on the side, right? They're giving you also the dimensions of those particular posts, 80 and 60 mil for both, or all three. Oh, sorry. So the aluminum is 60 and 50, whereas the steel is 80 and 60. What we're looking is the stress in each of these elements. So thinking about that boy or Aki van der Swing, what arrangement do you think this is? Is a series or parallel?
It's parallel, so
Exactly. Why is it parallel? You have to substantiate, you know. Anyone? Rafika, Cleo, Aiden, Pussy, why is it parallel?
Lengths are equal.
Not that. That does help. Yes.
You're adding the forces to get the total.
Yes. Exactly, because that 70 kilonewton per meter is being supported by those 3 posts, right? So the F total, I'm going to do it like this. Just watch me. So the first thing you must identify that is parallel. You write your relationships down, right? So F total equals F1 plus F2 or AB. And the change in length total, or you call it X again, total is X1 plus X2. So we can call one steel and we can call 2 aluminum. You could have also wrote aluminum there, just by the way. So I'm just using 1 and 2, it's just easy to manage. So clear. So first thing, they want to find the stress, right? So we obviously have to now find the force before we can find the stress, right? There's no force over here, the stress. How do we approach this? Before we do that, I wanted to work out the total force, right? So the total force is this UDL on top, right? Which is 70 kilonewton per meter. You guys have any idea how to make that into kilonewton? Anyone? Because normally they don't do it like this. They normally just give you the force. Anyway, should be easy. 70 kilonewton per meter. How do we get that into a force? Like straight kilonewton. That's what I'm asking.
So do you multiply it by 9.8? Because it's a load?
It's already in 9.8. Remember, it's kilonewton.
Oh.
So yeah. So, but what do we do then? It's per meter. Are you with me? So what do? We just times it by 5. Are you with me? 70 times 5. It's spanning over 5 meters. You know what I mean? Kilonewton meter per meter. And we're timesing it by meter. That and that cancel. Then it's just kilonewton. Are you guys with me? I hope you're with me. So therefore, 70 times 5 is going to be 300 and no, not 300. Yeah, what's it? 350. Amen. 350 kilonewton. So that's my total force. So it's going to be 350 equals F1 plus F, oh, just let me do this right, times 10 to the power 3 is F1 plus F2. All right, that's what we have now. Now the problem is we don't know F1 and F2. So what we're going to have to do is come to this equation over here. Okay, see this one over here?
Sorry, sir.
Now, sorry, Aiden, yeah.
Shouldn't it be 2 times F2 because there's 2
Yes,
aluminium
yes.
supposed.
Yes, you're right. We're going to get there. Don't worry. We're going to get there now. Don't worry. You're right. You're getting there. Yes. So what Aiden's going to say, we're going to say 2 times aluminium, right? But we're going to, you'll see how I'm going to make it work. Don't worry. So now, what we need now is relationships of forces over here. And what we're going to use is this equation. Okay. Oh, not x1 plus x2. Sorry, they're equal to each other. This is parallel. Let me just fix this. Yeah. So what we do here, we say x1 equals x2. Now, this relationship, I want you to write down. Now, I'll show you where it comes from. So, elastic modulus equals stress over strain. This is equal to force over area divided by X over L. You guys know flipping times? FA, you have to flip the bottom and top like this. Are you guys familiar with this? Flipping times, when you want to do that, that will be FL over AX, and that will equal E. Are you guys familiar with that math? The flipping times, you should be familiar. You guys
Yes,
got
sir.
that? Okay, perfect. So then what we're going to do, we're going to put this in terms of X. FLAX, where's my AX? But what this will look like, I'm not going to still do all the math, but you just times you on the other side, you cross multiplying, you end up with the extension equals something called flea, right? Just remember flea. So X is equal to FL divided by EA. You got that? So then you take that same equation and we do it for both sides here. So FL EA for steel, subscript 1, FLEA for the aluminium. 2 is going to come in now. So like I said to you, we don't have the force, right? We don't know the forces, so that'll be our unknown for now. But we're going to get a ratio between 2 forces. That's what we're going to do. So here we're going to say F1. But now, that being said, because the lengths are the same, no? They're all 3 meters. Mathematically speaking, I can divide both sides by L, by 3 meters, right? Are you with me? I can divide by L here and I can divide by L here. But they're both the same. And then therefore, you're just going to be left with F over EA equals F over EA. You guys with me? Right? So now all we have to do is find EA and EA for the steel and the, what is this? The aluminium. But as Aiden said, right, on the aluminium side, we're going to times it the area by 2. Reason being because you got 2 aluminiums. You could have done it by the force, but you can do it immediately over here. So let me do the first one for you. So F1 will be 200 GPa, right? And you're going to times that by the area of the steel. And that's going to be pi over 4. What is it again? 80 and 60. So that's going to be 0.08 squared minus 0.06. Remember, we're dealing with a what do you call it, section. You know, there's a hole in the middle, right? And then we say equal to F2. And then we're going to say that's going to be 90 gigapascals, which is on this side. And then it's going to be pi over 4. And then remember that it has its own dimension, which is 60 minus 50, which is going to be 0.06 squared minus 0.05 squared. However, now what we're going to do, we're going to times this by 2. Why are we timesing it by 2? Because we have 1 aluminium over here and another aluminium over here. You could have not times it by 2, you could have added another force here, but it's completely unnecessary. So we have 2 times the area of aluminium, hence we do that. So what I want you guys to do now is find this value under here, that value there, and I want you to find that value under here also. And what you're going to end up with is a ratio between F1 and F2. Are you guys with me? Is there any questions? Just work out that bottom section for me.
Yes, so how did you just divide the L and
Are you asking me why?
how do you get to just add it L to the denominator?
I'm dividing both sides by L. That's what I'm doing. What you do on the one side, you do on the other side. Are you with me?
Yes, sir,
If
but
I
I
have-
don't how do
if
you
I-
just add the L, sir?
Check this. 3x equals 3, right? Are you with me? You got
Yes,
that,
sir.
no? If I divide this side by 3, am I going to do the same side on the side over here?
Yes, sir.
So 3 divided by 3 will leave
So
me with
is
a
that
X.
because the lengths are the same?
Exactly, that's what I said, yeah.
Hmm.
That's why I'm doing that. To make it mathematically easy. Otherwise, you're typing in the 3 the whole time. Are you with me? Which is unnecessary. So then you have 3 divided by 3, which is equal to what? 1, right? You got it.
Yes,
Is that
sir.
enough, no? So I'm not adding an L, I'm just dividing by L. You know, I'm dividing by 3. I don't know if I'm making sense. Just to make it easy, just to remove the L's. So that we don't have to type in L again. Like, you know, otherwise you must put in the 3 here and you must still put in the 3 here, which you don't need to do. And we're doing that because the lengths are the same. And they typically are always the same. Yeah. Otherwise it's not
So-
parallel.
Okay, so then for all these calculations in parallel, sir, we'll take the
Yes.
length out.
That's correct, yeah. You'll see that yourself. Otherwise the change of length will not be equal, if that makes sense. You know what I mean? How can it be the same?
Yes, sir.
Yeah, okay. So let's quickly get those values at the bottom there. Let's move. Lucy, Theo, you guys are normally quick.
439,823 times
Okay,
10
but
to the
just get
power 6.
this side here, no? This side here.
Yes, sir.
Yeah. Say 4,
That's correct.
yeah,
439,823.
439. Yeah, that's fine.
Times
Power
10
6,
to
no?
the power 6. Yeah.
Okay, the other side.
I haven't calculated the other side.
Okay, let's do the other side quickly. Strength of materials is a very jealous subject, no? I'm just making you guys aware. Very jealous. Wants
I
a
got
lot of
3.
attention. Yeah.
I got 3455.191 times 10 to the power 3.
Okay, give me like 3 decimal places. 3, 4, 5.
Yeah, 345.5.
Point.
Yes.
0.5. Yes.
0.575
Yes. That's
times
fine.
10 to the
Okay.
times 10 to the
Okay,
power
cool.
6.
Yeah. So what I want now is you to make a ratio between the two. You can decide which one you want to do. So let's say you're at times the 439 on this side. You know what I mean? Cross multiply, man. You know what I mean? But just cross multiply this on the side. So I want F1 equals some number to F2. Are you guys with me?
Okay.
So
Yes,
find
sir.
that number. Yeah. To be successful in the subject, your mathematical ability is of the utmost, is of cardinal importance. So make sure you're practicing your math skills. Yeah, it's a lot of math. So Aiden, if you had plans to drink this weekend, cancel them.
Nah, sir,
Okay.
not really.
Okay, let's just get the ratio. I was going to check in the book quickly what we should get.
I got 1.272.
Okay.
7. F1 is equal
1.27.
to 1.272 F2.
1.272. Perfect. Can we get it? Can we?
If
Cleo is a reliable source, but can we just quickly confirm? So yeah, 439. That does look around with right. Okay. There is another way to do this, by the way, but I'm just sticking with. Yeah. Anyway, get back to that. Are we happy with this? We all get that ratio? I was going to move on before.
So would this question be basically under gradually applied loads or
This is under the,
sudden?
it's under the compound bars, but I don't think the strain energy does that part yet, man. They don't do parallel, but it does come in the next chapter though, in chapter 3. Yeah.
Okay.
But the series part is there in. You'll see if we do it. Yeah.
Okay.
Yeah. There is a parallel component, but I don't think the N5 books look at parallel systems in that gradually applied stuff. Yeah. Okay. So anyway, let me move on. Time is going. So we get the 1.272. So what I'm saying, you see this over here, we now revert back to this equation over here. This one over here. So we can say this was this one over here. Okay. I'm subbing back in here. So let me write it down for you. So it's 350 times 10 to the power 3 equals F1 plus F2, right? But now, like I said to you, you want to substitute F1 over here, right? So our only unknown is F2. Is it clear to everyone? Doesn't make mathematical sense. That's what's important here. There is a quicker way to get the stresses, but let me do this way. So F1 is 1.272 F2 plus F2. Aiden, can you see that now? We don't need to times things by 2 because you already done it before. I don't know if you're with me. Yeah. And you take F2 as a common factor, right? And you take F2 as a common factor, there'll be 1.272 plus 1. Got that? Making that 350, not 356. 350 power 3 divided by 1.1. Oh, sorry, it's going to be 2.272. Obviously, you're just adding 1 there. And that'll give me the answer of F2. And F2 is the force in the aluminium. Can we quickly get that?
Okay. 154 times 10 to the power 3.
Exactly. 154 times, was it exactly clean? 154 point? Or...
Yes. Yes, it's 154 kilonewtons.
Okay, perfect. Thank you. So we can say time, I'll just call it kilo. And all we do, to find F1, we must then multiply 1.272 by, you know what I mean, by this here, because F1 is that. So that's 1.272 times 154 kilonewton. And what do we get for that? Who's here? I hope you're still there. Yeah.
195 or 191, sorry, 195.
Yeah.
0.99 or
Okay.
196 newtons.
That's fine.
Kilonewtons, sorry.
Okay, perfect. So now you've got F1 and F2, right? But you're not done. You called for steel, which is always the case. I think it's worth mentioning. See, determine stress brought out in each one. And all we do is go back to our relationships before. So we know that stress 1 is going to be the steel. I hope you guys are with me here. And the aluminium is going to be stress number 2. So we just say force over area. But you must make sure we we're using the right areas, right? That's obvious, I think. Force 1 is going to be 195.99 times 10 to the power 3. And obviously, if you store your values like Cleo mentioned in the previous thing, it would have been easier to, you know what I mean? You can just recall A again, you know what I mean? If you did that. So in this case, so there's 80 and 60.
Oh.
So what is the diameters again, sir? So you muted, sir. So
Which diameters do you need?
I'm waiting for the diameters. Does anyone have the diameter?
Diameter of aluminium or steel?
Oh, sorry guys, 80 and 60. My
Oh.
mic was muted. Yeah, my bad.
So which one's
Thank you.
80, sir?
It's 80 and 60. Remember it's a hole. I lost my thing now. 80 and 60. It's like an internal. Remember it's internal. It's like a round section, man. So that's what. Can't believe when was this? This was now, man. 80 and 60. Yeah.
So is that for steel?
Yes, that's correct. Okay. How is it this here? Okay. Okay, yeah. I thought I lost my whiteboard now. I was panicking. Okay, let me quickly share this. Yeah, it's 80 and 60. That's correct. Yeah. So the questions, yeah. So over here, come back here. I believe you guys can hear me and see the board. Power for 0.08 squared minus 0.06 squared over here. And then for did we get that one? And the other one was the aluminium was 154 or just kilonewton. And then we're just dividing that by that diameters were 60 and 50.
For the first one, I got 89,122.
Let me check the answers. 89.
89,122 megapascals.
Doesn't seem correct. Let me just check here.
So I got 89.104.
I got
Why?
8672. Yes.
I'm just checking. So I'm looking at the book now. I'm not seeing the same. Let me just confirm something here. I'm assuming that these values are right here, no? These values over here are right. These values over here are right. Let me just quickly see. Okay. So I'm gonna just quickly do that first one. It's gonna be 350 divided by that, and it's gonna be 2.272. Okay, I do get the 154.049. That's fine. Then I say 154 divided by pi over 4. Hope you guys got the right diameters. Okay, and then bracket 0.08 squared. Squared minus 0.06 squared. And how much you guys get for the for the stress?
Stress for steel is 89,122.
Okay, I'm using the wrong value. So okay, 195. Because I'm seeing a slightly different value from the book, which is disturbing me. So 195.99.
I got 88672.
Okay. Yeah, but I'm gonna just check now. I'm hoping I didn't. Yeah, so I'm getting 80. Yeah. Okay. I'm getting 80 for this one. Like 80.80. I didn't add the 0.99. Let me add the 0.99. So there should be 80.722 megapascals. Okay. You guys get that one? That's
No.
not looking like the book.
No, sir.
So what did you guys want to do? Do not square these values. So wait. 86.
89,
86.85.
sir.
89, sir.
89. I have
I got 88.
86. Are we using the same values here? So
Yes, sir.
195.99 power 3, power over 4,
Yes.
0.08 squared minus 0.06 squared. Not even the same as the book, which I'm concerned of now, because it should be 86.585. I must look at something now. I'll check it now. Yeah. I get 86. I'm not sure. Sorry guys. I see what I did. Yeah, it's 89. It's 89. Definitely 89. Yeah. Okay, perfect. Okay, cool. 89.122 megapascals,
Yes.
right?
Yes.
I'm still worried because I'm not getting the Deutsch answer. I'm just have a look now, it's wrong. So what you must do now, you do exactly the same for the aluminium. However, remember you're working with 2 times again the area. So you must times that by 2. So that's going to be 0.06 squared minus 0.05 squared. I'm just going to check what's going on here, man. Something is bothering me. Because we definitely did the right thing. So I just want to check over here with my ratios over here. If these ratios are right. I hope you guys did this right here. Okay. So F1 to 100 GPa. You guys can manage with the second force along, no? Is that fine? I'm just verifying this value here, this line over here, because this could be the problem. This ratio could be the problem. 5 over 4, 0.08 squared minus 0.06. Yeah, 439.8. That's power 6 over here. That's correct. And then on the other side, it's going to be 6 and 5. Okay. 6 and 5. But we're timesing it by 2, no? Do we have to times by 2 now? But it's the same. Is this the problem? I think I know what the problem is. I see. So this one is wrong, colleagues. Cleo, Aki, Boosie. You guys didn't times this by 90 over here. You guys kept it as 200. That's the problem. You see over here?
Where, sir?
Over here. So when you put this in, this was because you put 200, man. So remember, they have 2 different elastic moduluses. This is supposed to be 90 over here.
Oh, yes.
Yeah,
Yes.
see? So this should be
80.
155. Yeah, 155. Yeah, there we go. So this is 155 now. 155.508. So ratios are different again. So yeah, we have to kind of go back now. But the principle is still the same, so it's fine. 508 times 10 to the power 6. Then I'll give you your new. So it's good that it happens because now you can see that, be aware that it's 2 different materials. If it's the same material, it's going to be fine. So 1558.508 power 6. And your ratio should have actually been 2.8. 2.8. Perfect. It's fine as long as you're conscious of that mistake so you don't do it again. And we just remove this. Students, I hope you're all with me in terms of what happened there.
So can you just tell me what is the diameters by the aluminium, please?
That's 50 and 60 millimeters. Yeah.
Yes.
Okay. But I hope you guys are following what we did there, no? Just for this one. So make sure you always verify your ease. Consequently, this will be now 3. What's it now? 3.8 something. Yeah, I'm all our values are basically going to change now. 3.8 to 8. I could have said 3.83 by the way. Let me just add the 3 in, just to be a bit more accurate. It's a 3 here. Therefore, that's going to be 350 over that. 3.8 to 83. And our force 2 should have been 91. Okay, it's 91. Perfect. 91.424 is fine. Yeah, I think we sorted now. Kilonewton. And I'm just going to erase all of this. Obviously, you know what to do there. We take that same thing, 91 point something times, what is it ratio again? 2.8 283. Then we should get 258 for the steel. Okay. And that's 576 kilonewton. Okay, quite. Obviously, you must just modify these values now. Is it okay with everyone? You just got to just change that one. You got to change that one now. Students, are we on the same page now? Just fix the error there on top. And it's supposed to change. Are you guys sorted? Shall I give you the answer for this one, for the steel? So long. Are you all understanding what's going on?
Yes, sir.
Okay, perfect. If you're not, please say something. And the area, so the stress for the steel, obviously this can be the 258. I'm not going to write it in there. So you can just put in F1 for me there and F2. Just make sure you're again timesing by 2 for the aluminium, because there's 2 of them. And this is going to be 0.08 squared minus 0.06 squared. And you should get 117.583. There we go. And I want to say something about that. And then the other one was using this correct forces is 91.424. Change my, yes. Anyway, that stress should be 52.912 megapascals. Okay. Are we all on the same page? That should be that. That's the correct answers. Yeah. Lucy, Akif, Cleo, Rafika, and Aiden, I believe. I don't know who else is here. Didn't check. Timpiwe, yeah. That's everyone. Guys, are we good? Is there any questions? Because we're going to actually end off now. Yeah. I mean, we're over our time and yeah, it's a pity.
I'm still a bit lost there, but I will catch up.
Okay, so where you lost? Let me answer it now. You can just ask. You can ask me now. You don't need to be lost.
No, I'm lost very fast. They're there by 90. The 90 that you said we must add.
This one. Okay, let me come back. So if you go back to the question here, right? So remember I told you just now that different materials have different elastic modulus. You see the one in the middle is steel. You see there 200 gigapascals. You see there? Aluminium has an E of 90. Are you with me?
Okay, yeah.
So what I'm saying is that, can you see the E over here and the E over there should be different. So it's 290. So you guys, you kept the 200 over here. You understand? That's why we got that 3, 4 something.
Okay.
You got it now?
Yes, yes.
Obviously that affected everything. So what I'm saying is be aware that when the materials are different, there are different E values or elastic moduluses. Okay. Anyone else? And back to what Cleo asked about tension and compression. Can I ask you guys, looking at this thing, are these beams in tension or are they in compression?
I think that's compression, sir.
100%. They're being compressed. And so all you can do and be cute, you can just put a nice C, bracket C, like this. Or you can even write compressor. It's a very
So
important thing.
can I just say why they're in compression?
Okay, do you want to use logic here? Look at this. Let's think of something at home. What can we think of? So this is supported like this, right? Are you with me? Like so it's supported at the bottom. Think of a light bulb. You know what I mean? Or a tree. You know, something with it's fixed at the
Yeah.
bottom. You know what I mean?
Yes.
Are you with me, Cleo? So if I do this, I make two of them and I put a load on top of it, right? Well, think of a table. If I put weight on the table, these things are being compressed with this one force like that and another force like that.
Oh,
You see,
okay.
you got me.
Yes.
If it was intention,
Got you.
it would have been the other way around. You check. So like
Mm.
you're pulling it. Tension is like pulling. Compressing is like squeezing. Am I right? Squeezing? I think so. Yeah, something like that. Okay.
So if you look at it
and-
in terms of the values, what do you look at? So do you look at the stress or the extension?
You're asking a good point. So you want to look at the stress. So on a practical sense, this is what this means, right? These are the stresses induced now due to that force. Now, if I had to look at the allowable, if I had to look at the yield stress for these things now, so let's say my yield stress value, my allowable stress. So like when you buy material comes with like a standard stress. So let's say your allowable stress, like that certificate, man. Let's say it was for steel, it was 275, and for aluminum it was 100 MPa. As long as these values are less than these values, the structure will be fine. Is it clear to everyone? So what I'm saying is that if we load this thing further, right, we put more weight on it, you're going to find that these values are going to increase. So if this value exceeds 275, do you know what that means? It's going to start to deform. Is it clear to everyone? Think about the tension graph. Are you with me?
Yes, sir.
So what I'm saying is, when you buy the material, it'll tell you, okay, this thing can handle 100 MPa for the aluminium, and the steel can only handle 275, as an example. So with our current loading condition, we are well below that. Can you see that? We are 117 and 52. But if we change that 70 kilonewton per meter to maybe like 150 or 200 kilonewton per meter, you'll notice the stress values will increase, right? And if it increases above that value, if it increases above the UTS, it'll break. That's the purpose of these calculations, by the way. Yeah. I don't know if I was clear there. So to verify if the extensions are the same, I'll show you quickly now, then you'll end off. So we know that X total is equal to X1 plus X, plus equals to X2. So all you can do is say X1 is the steel, right? You can just call it XS. You can just plug and play FLEA, right? If you plug that values in, you get an extension value, right? In millimeters. Do it for me and then put it on the group. Then you do exactly the same for the aluminium, but you must use F2, right? Keep everything the same. You must use the lens here. You keep the L's are the same, E2, A2, right? And you notice that the extensions will come out to exactly the same value. That means that they both extended the same amount of value under that particular force. That's how you know it's in parallel as well. Okay. So guys, I think we're done for today. It's a lot. Is there any questions before I end of the session?
So is this a module 2 session, sir?
Module 1. You guys are gonna have to push on module 2. I have module 2 recordings as well. Because what I'm doing now is that I'm having sessions every 2 weeks basically now. So you guys cover some stuff, but what I realized is that you guys must put in the work. Like what I'd like is this. You guys work through the stuff and you guys give me some questions to work through. Is that fine? Or I can bring questions. You know what I mean? Then we can solve.
So
I don't
can
know
you
what
give
you
us
guys prefer.
questions, sir?
Okay, so all that questions, right, is on the Google Classroom. Are you with me? And I have recordings for each and everything. But what I'm saying is that if you have problems with certain stuff, I can resolve them if you'd like. But I like taking different questions so you can, because you already have that answers there. You know what I mean? But whatever
Yes, sir.
suggestions you have to support you, just tell me in the group. Are you with me?
Yes, sir.
Yes, sir, I'm struggling with this. I can come. Or, sir, let's try this. As long as I'm supporting you. But I just want to get the questions in time so I can prepare for it and just navigate on, okay, you know, what questions can I ask you? You know, it's just many things, man. Yeah. But anyway. But for the tests, my tests, make sure you practice past papers, I would say from 2020 to 2024 or 2021 to 2024. So for instance, what I'm saying is go to the past paper of 2020 or 2021. Question 1, do that one. Go to question 2. Go to the next paper in the same paper, do that next question. You understand? Practice like that. Right? But keep on the same section. Module 1, do those stuff. Then module 2, go to the next question. I hope I'm being clear for that
No
kind of
problem,
practice.
sir.
But
Sir,
what I can
could
tell you, yeah.
Could you send the recording of module 2, please?
Okay, don't worry. I'll send it there. Just remind me in the group. Yeah, then I'll send it there. But what I'm telling you now, this requires a lot of work. So yeah, just letting you know. Yeah. Okay. Is there anything else, guys, before we close off?
Thank you, sir.
Okay. Okay. Cheers, guys. I'll
Thank
talk
you.
to you again.
Okay.
Yeah. Cheers. Bye.
Bye. Sorry, when is the next class?
So you guys are writing next week, I think. No? Is that correct? Thanks, Aiden.
Yes.
So we might have a class probably on